Hello everyone, I'm Richard Chen from George Mason. Today I'm going to present my final project for CS 682 computer vision. My project title is Magic String Network-Friendly Holographic Telepresence via Semantic Communication. Volumetric video actually is really allowing viewers to adjust their viewing direction and navigate freely in 3D space, granting them the 6DF motion. Such flexibility enables numerous applications in entertainment, healthcare, education, and it has been envisioned as the top case of 6G. So here's a video demonstrating what's the volumetric video. As you can see, with different viewport, no matter in different position orientation, the viewer content will be changed based on the viewer's viewport, which we call it as a 6DF video. So in the traditional approach to transmit 3D volumetric video, it involves transmitting the point cloud or 3D or 3D mesh. But the problem of such approach is that it consumes a huge bandwidth. So in this project, my idea is to leverage the idea of the semantic communication, which we transmit only the pivotal information, because it can drastically reduce the internet bandwidth demands. And essentially, the semantic communication is an encoder-decoder problem. So the key challenges are the first is how to properly and accurately encode semantics in real time, and the second challenge is how to decode volumetric representations from extractive semantics with high visual quality in real time. So in this project, I decompose the encoder of the user into the motion semantics and the color semantics. And at the receiver side, we decode the motion semantics into the body movements of the user, and decode the color semantics into the perceived color of the user. Then we combine them to become the hologram of the user, which means that we reconstruct the remote users in a high fidelity. So specifically, at the entrance system involved, we have multiple RGB cameras to capture the remote users. Then we use the key point to denote the motion semantics, and then using the lightning estimation to encode the lightning semantics. Because the idea behind this approach is that the body movements are essentially driven by the articulation of the bones and the joints, which are inherently complex. But our insight is that checking the position of specific important points, known as the key points in the human body, such as joints, provide a sufficient basis of the model user's movements. And in terms of lightning estimation, our insight is that the perceived color of the remote user is a combination of the base color and their skin, which refers to the original color before applying any lightning effects in the computer graphics. So if we assume that the remote user's base color does not change during telepresence, representing color semantics is equivalent to encoding the lightning characteristics of the scene. Then our first decoder is to decode the key points into the sample X. Simple X is a parametric human model that can precisely represent the human movements over time. So during the internet, we will transmit only the simple X parameters and the lightning characteristics, and their data size is super low. So in this way, we can reduce the bandwidth demands over the internet. So at the decoder side, at the receiver side, our decoder tool is that we have the base color of the human body, and we combine them with the simple X parameters, lightning characteristics, to get a coarse-grained rendering. So because we want to have a fine-grained rendering, so we did a neural rendering model. But the problem is that we need to execute under 30 FPS, which means that our budget for each frame is only 33 milliseconds. But the overhead of rendering is huge. So our design approach is that we we detect the significant movements of the human body, and then we update only the change part which have the significant motions, and then we put only this part into the neural rendering to update the final results. So in this way, we can reduce the rendering overhead to accelerate the neural rendering approach. So let's take a look at about the evaluation. Our baseline is a point cloud based streaming. This is a work published in the ACM Mobilicon 2023. And the first evaluation is the bandwidth. As we can see, the magic string consumes only 0.2 megabits per second, but the meta string consumes over 70% megabits per second, which means that we achieve around 350 times bandwidth reduction. And in terms of latency, magic string can achieve less than 100 millisecond entry latency. However, the meta string requires around 170 millisecond latency, entry latency. We next evaluate the throughput, latency, FPS, and the SSM of magic string and the meta string with small points, because in the original design, the meta string only string like 300K points. Now we want to know what will happen if we string meta string with more points. So we can observe that basically with more streaming points, the throughput of the meta string will increase significantly. For example, when we string 1000K, which is 1 million points in meta string, it will consume around 400 megabits per second bandwidth. And also, streaming more points, it will increase the entry latency, because it will increase the transmission delay and increase the processing delay. And it will also decrease, and the streaming more points will also decrease the FPS, because it will increase the rendering overhead at the receiver side, which is the MR headset. And in terms of SSM, we can observe that when we stream more points, meta string can achieve a larger SSM. And we can see the magic string achieves the similar SSM about our meta string with 700K points. However, we can notice that even though at this setup the SSM is similar, the meta string requires 250 megabits per second throughput. However, magic string requires only 0.2 megabits per second. Also, in terms of latency, the meta string requires around 60 milliseconds, but the magic string requires only 0.1 second. And note that the latency here is the transmission delay. And then finally, we evaluate the qualitative results. And A is magic string, B is meta string. As we can see, meta string achieves photorealistic rendering, but the meta string, which use the point cloud to represent the human body, and their visual quality is bad. And sometimes we can observe some black area in the human body, which may refers to that under certain scenarios, for example, the high lightning, with a very strong lightning environment, the depth estimation may be not very accurate. So in such scenario, the point cloud based streaming will tend to have a black spot. And overall, the visual quality, the qualitative compression of the magic string is way better than the meta string. And this is end of my presentation. Thank you for listening.